Hello, my name is Müller. Thanks for giving me the opportunity to present our project, Learning Robust Models using the principle of independent causal mechanisms at a GCPR conference. This is joint work with Schmier, Lynton, Ardizzone, Carsten, Rother and Ullrich, Köthe. We are collaborators at University Heidelberg. In this work we consider one of the most important problems in machine learning, generalization. Consider the following example. We want to learn a model that predicts the class of an animal from an image. In supervised learning, we are given a training set and train our model thereon. Here we see that there are images of cows in our training set. The goal is to make good predictions for unseen samples that follow the same distribution as the training set. In our example, the cow in the test set does not exist in the training set, but it is from the same distribution, for instance, same kind of background. This is one form of generalization. But there's also a second one that goes beyond the classical supervised learning setting. In many real-world applications, the unseen samples do not follow the same distribution as the training set. In this case, we want to generalize beyond the dataset distribution. This is sometimes called out-of-distribution generalization. In the example, the image of the cow has a different background and therefore the image is not in distribution. Supervised learning has achieved remarkable results in the last years. Therefore, we can raise the question, do these results translate to out-of-distribution generalization? Empirically, this is not the case. The cow in the upper left, for instance, is correctly classified as a cow, since it comes from the same distribution as the training instances. However, if we consider an image of a cow with a different background than the training instances, here beach, the classifier fails, since it relies on background for prediction. The cat in the lower left is correctly classified as a cat. However, if we overlay the image with an elephant texture, the classifier fails to predict the correct class. In this case, the classifier relies on texture for prediction. It is known that machine learning algorithms use shortcuts that the dataset provides in order to solve the task. In this case, background and texture are sufficient to solve the task, and therefore shortcuts that the model might use. Both background and texture have a non-stable relation to the class of the image. Therefore, the classifier is not robust. Our goal is to find relations to the target variable that are stable in order to improve robustness. In this work, we consider the setting of domain generalization in order to improve robustness. Assume to observe a system in different environments, or expressed slightly differently, some related datasets with input-output samples. The task is to go beyond the classical supervised learning task, namely to make not only good predictions for the seen environments, but also for the unseen ones. Here in this example, we have datasets of animals in Austria, Ireland and Argentina, where we can train our model. The goal is to make good predictions for animals from an unseen country like South Africa. It is important that the datasets differ sufficiently enough for domain generalization to work. If all datasets are the same, we are in the supervised learning setting. In this work, we take a causal perspective on the problem of domain generalization. The simplest causal model one can think of is a model consisting of two variables. In this example, we have different temperature measurement devices that measure the temperature at different heights. It is easy to see that height causes the temperature. When we go up, the temperature goes down. But when we heat the devices, they do not change in height. The causal factorization of the joint distribution goes along this direction. The joint distribution is the product of the prior of the height times the conditional probability of temperature given height. The principle of independence of cause and mechanism states that we can change one causal factor independently of the others. So if we put our measurement devices to Austria, the heights might change, but the mechanism relating height to temperature does not change. Similarly, if we put the devices to Liechtenstein, the distribution of heights changes, but the mechanism relating height to temperature remains the same. The reason for that is that the mechanism is inherent in nature, and physics works in Liechtenstein as in Austria. Of course, this only works because both countries are in the same climate zone. If we consider measurements over time, let's say hundreds or thousands of years, the height remains the same, but due to climate change, the mechanism relating height and temperature changes. In both examples, one causal factor is changed, leaving the other unchanged. If we factorize the joint distribution in the non-causal direction using the chain rule of probability, then we do not have any guarantees about the independence of the factors. One can even observe empirically that if we change the distribution of the height, then both factors in the non-causal factorization changes. In a general version, the principle of ICM states that each causal factor can be manipulated without changing the other factors. Therefore, if we know something about the underlying causality and we interact with the underlying causal system, the causal factors that are untouched by the interaction can be reused, for instance, as in the example above. This is the reason why we want to learn about the causal system of the dataset. Factors that are unchanged can be reused, for instance, for prediction. Now we can deduce the assumptions coming from this consideration. The conditional probability of the animal classes given only the background like grass differs due to country. Here E could stand for Ireland and E prime for Argentina. This might be because the cows have to choose the background differently according to their location. So in this case the relation is not stable. However, the relation what constitutes a cow to the class label should be stable across all environments. A simplified causal graph could look like this. What constitutes the cow, like shape, causes the label. This relation is stable across all environments. The association between cow and background is an unstable relation and influenced by the location and therefore unsuited for prediction. We propose therefore one assumption. The relation between the direct causes, here denoted with the subscript parents of y, and the target variable is a stable relation across all environments. This is denoted with y independent of e given the direct causes. The goal of domain generalization is to find features that are maximally predictive or informative about y, while satisfying the invariance constraint at the same time. In the example, a classifier trained this way would exclude the background information from prediction and only use the stable relation, in this case, what constitutes a cow. So how do we achieve this goal? How do we make it amenable to gradient-based learning? We relax the problem by making the hard constraint a soft constraint with an invariance loss that measures how well our invariance constraint is satisfied. The mutual information term can be optimized by a loss denoted as L0 and normalizing flows. I will not detail this here, but details can be found in the paper. It is important to note here that this approach is model agnostic with respect to the data generating process. So we do not make assumptions about how variables are related like linearity. So how do we define the invariance loss? In the paper we showed the following theoretical result from which we derived the invariance loss. Assume that we have a function that is invertible and differentiable in the target variable y conditioned on the features h. The theorem states that when the output of this function is independent of the environment and the features, the invariance constraint is satisfied. This means the features have an invariant relation to y across all environments. Normalizing flows satisfy the invertibility condition in the theorem, and therefore we also employ them in this work. In order to make the theorem tangible for gradient-based optimization, we have to ask how can we enforce the constraint in the theorem. We use a kernel-based independence measurement called Hilbert-Schmidt independence criterion, or shortly HSIC, that takes two distributions as input and returns 0 if and only if both distributions are independent. We take the HSIC to define our invariance loss. The HSIC gets as input both distributions from the condition in the theorem. So if this loss is 0, the conditions in the theorem are satisfied and therefore the invariance constraint follows. This allows us to optimize the domain generalization objective in a gradient-based manner. I reasoned above that the domain generalization task is a causal discovery task. We proved in the paper also a discovery result. Assume that our feature extractors h perform a variable selection. One can think of this as a gating function that is either 0 or 1 for each input variable. We then showed that if we optimize our domain generalization objective, then the feature extractors return the direct causes of the target variable y. So we can identify the direct causes from y under suitable conditions. Of course, this is not trainable by gradient-based methods if we go naively about this task due to the variable selection. However, some prior work showed that it is possible using certain reparameterization tricks. We used the differentiable gating architecture for some of our experiments too. In the following, I will show you two proof-of-concept experiments. In the first experiment, we aim to find the direct causes of y from 5 input variables and solve the domain generalization task. In this case, we are in the regression setting and not in the classification setting. We assume that we are given 3 environments for training and 1 for testing. We create a lot of diverse scenarios, for instance different causal graphs that generate the data. We create also diverse scenarios by choosing mechanisms that relate the variables of different complexities. Here I just want to show you one result. On the y-axis you see the detection accuracy of the direct causes of y. On the x-axis you can see results for the mechanisms relating the variables. For instance, L stands for linear and M for multiplicative noise. Our methods, the red and green one, achieve good results for all mechanisms. The green one is the general approach I showed in this talk, and the red one a special case that makes assumption on the underlying data generating model and is basically an L2 with the invariance loss. The orange one is ICP, one prominent algorithm that makes use of differences between environments and relies on the linearity assumption. It shows good results in the linear case, but fails when the mechanisms get more complex. The PC algorithm is a classical causal discovery algorithm, and here shown in blue. It shows poor performances for all mechanisms. As a second experiment, we consider a modified MNIST dataset. In this dataset we only have 2 classes, 0 for digits smaller or equal than 4, and 1 for all other digits. The shape of the digits is the cause for the label, and therefore the stable relation we are looking for. In this dataset, noise is added to the shape-label relation, and in only 75% of all cases are they correctly associated. In the first environment, the color of the digits has a stronger association to the label, namely 90%. This means red is in 90% correctly associated to the first class and green in 90% to the second class. Also in the second environment, the color has a stronger association than the shape, namely 80%. In the first 2 environments, color is a better predictor for the label than the shape, but the relation between color and shape is not stable. In the third unseen environment, the association of color is reversed. So when we train a standard classifier on this dataset, we see very good performance on the first 2 environments, but bad performance on the third environment. The classifier relies on the color for prediction. Color is the best predictor for the first 2 environments, but a bad predictor for the unseen one. Our classifier, in contrast, shows good performances in all environments and learns to use only the stable signals that show across the first 2 environments, in this case shape. We also showed results for different values of lambda, the hyperparameter that regulates the influence of the invariance loss. We can see several things from the plot. First, robustness and goodness of fit is a trade-off. If lambda is small, we have very good performances in the seen environments, but bad performance in the unseen one. If we increase lambda, then we get better robustness, but the performance gets worse, especially in the seen environment. We can also see from the plot that we achieve good results for a broad range of lambdas. So both experiments show that the method we propose is able to find the stable relations that promise robustness for unseen environments. In this work, we proposed an approach to domain generalization that is model agnostic and therefore refrains from assumptions like linearity or additive noise on the data generating model. This approach formulates the domain generalization task as a causal discovery problem with differentiable information theoretic concepts based on the principle of ICM. Thanks for your attention. I'm happy to take questions.